My exposition is multi-criteria decision making supporting with optimized multi-factor combinatory analysis. Volodymyr Riznyk and Sydorenko. Lviv Polytechnic National University. Representation and definitions. The MCDM problem can be represented in the criterion space or the decision space. Alternatively, if different criteria are combined by a weight linear function, it is also possible to represent the problem in the weight space. Below we are a demonstration of the criteria and weight spaces, as well as some formal definitions. Modern method of multi-criteria decision making, as well as multi-criteria decision analysis, are the most accurate methods of decision making, and they can be known as a revolution in the field. A list of application fields are and appropriate examples of the application focus. The left column is application field, and the right column examples of the application focus. Education include, for example, contextual learning, modeling in a personalized and ubiquitous learning, and education learning, career and job. You can see in the right column, it is, for example, occupational stressors among factors and other problems. The supply chain management include the supporting sustainable supplier selection, a green supplier, and evaluation and selection, and so on. Civil engineering, please see on the right column. Financial and economics and energy sector, engineering and production, and organization and corporatives. To see this slide, you can see definition of the ideal ring bundles, an end-stage ring sequences of natural numbers for which the set of all sums or consecutive terms in the ring sequences consists of the numbers from 1 to n multiplied by n minus 1 plus 1. Each number occurring exactly once is called ideal ring bundles, shortly IRB. Here is a graphical representation of an ideal ring bundle containing 5 elements: 1, 3, 10, 2, and 5. Application of ideal ring bundles for optimal multifactorial planning of experiments. An optimal combinatory plan of experiment is known and can be developed using the so-called Latin squares and their complete sets. A Latin square or order P forms matrix which contains each symbol in each row and column exactly once. Two Latin squares of order P are called multi-orthogonal Latin square or Latin or Greek square. The maximum number of factors under the study F, the maximum number of level row R and for each of these factors, and the maximum number N of pairwise orthogonal Latin squares of the order M, which forms the matrix M and multiplied M. Chosen to build an optimal plan for a multivariate experiment are interconnected by a system of simple equations, as you can see. F is equal R and equal to number of ideal ring boundless elements. N is equal, you can see, minus 1 and in M is equal minus 1. The next slide is the optimal combinatorial measurement plan based on the elements can be generated using the next calculating actions. The first, form based on n sequences of numbers, K1, 2, and so on. The IRV of order n built an auxiliary matrix of numerical symbols P for numbering rows of Latin squares. The next calculation actions you can see on this slide, and the next you can see a synthesis of optimal multifactorial plans of experiments. As an example of the implementation of the removal algorithm, we construct a sound system of pairwise orthogonal Latin squares based on B 1, 3, 10, 5, where K is equal 1, and so on. And you can see the set pair for numeration of Latin square rows. The set C for numerical of Latin square columns, so-called C matrix, you can see. And the next we can see the set M1 for finding the complete set of Latin squares. The set M2 for finding the complete set of Latin squares. And the last set M3 for finding the complete set of Latin squares. According to the coordinates of the sets P and C, we construct Latin square Q1, Q2, and Q3. You can see the squares form a complete set, all family of the matrix to design n factors of order n equal to 5. Optimal measure plan, each factor can have 4 levels. The optimal plan of experiments is 5 influence factors you can see on this slide. Here you can see number of experiments 1, 2, 3, and last 16. And number factors on the left column, A, B, C, D, E. Example of pairwise orthogonal Latin squares applications of material selection for optimal design combinatorial analysis with 5 influence factors. Experiments number from 1 to 16, and results of experiments you can see are under the plan of experiment. Criterion X, criterion Y, criterion Z, you can see as the results of experiments. Conclusion. The application of IRBs in fuzzy decision analysis provides for the minimizing of experiments while maintaining on validity of the analysis. It is possible to use a simple algorithm to design the optimal multifactorial plan of experiments in matrix form. The proposed algorithm can be well applicable for analysis of the influence of a lot of physical parameters, as well as some other factors on the behavior of the analyzed fuzzy object or its model. This approach makes it possible to provide sufficiently less of computing in fuzzy decision analysis while maintaining on validity of the analysis. The application of the ideal unbundles provides for finding optimal solution problems by reducing the volume of the experiments in fuzzy decision analysis while maintaining on validity of the analysis. It is possible to use a simple algorithm to decision of optimized multi-factor combinatorial analysis for multi-criteria decision making support. Thank you.